right, so the first thing I do to find the tension in each chord is pick a place on the object or in the system that I want to sum all the forces. So imagine the string is attached, the strings are attached to the rectangular object at that one place at the top of the object. Now, these two angles are the same, so you can probably make an estimation as to what you think the tensions should be or should be like. Any ideas? Equal? So equal tensions, you expect them to have equal angles, expect them to have equal tension. So let's see if that's true. Those sort of assessments that you can make on a system, about a system, will help you answer like multiple choice questions quickly, or those do you agree or disagree with the student's claim questions easily if you can begin to see beyond the numbers and think about the big picture. So first you want to draw the free body diagram. I always abbreviated FBD. So here's the knot or the place where all of the forces are acting. There's definitely a weight force acting on this system because there's a hanging mass of 50 grams. So F sub G. Now if I use 10 as the gravitational acceleration, that's cheating a bit, but it makes the math easier. So we'll just call it 500 newtons. But then there are these two chords that are attached to it too. So I'm going to call this one FT1 and this other one FT2. So that represents that it's a force and it's a tension force, and 2 because it's the second one, and this one was the first one. Now, let's see. Geometry-wise, if this is parallel to the ceiling there, then if this is a 45-degree angle, then that should be 45 degrees. And if this is 45 degrees, then that should be 45 degrees. So then over here on my free body diagram, I can create an x-axis and label this as 45 degrees and 45 degrees. So now when I look at this, I've got this x-axis or x-reference axis and a y that goes up and down. So the system should be in equilibrium, and if it's in equilibrium, then the sum of all the forces in the x direction should be equal to 0, and the sum of all the forces in the y direction should be equal to 0. Now when I look at this first tension right here, tension 1, I see that it has a component, or it's pulling the picture frame or the box or whatever that is. It's pulling it to the left a little bit. FT2 is pulling it to the right a little bit. Does the weight force pull it at all in the x direction? No. So how do you want to define left and right numerically or mathematically? With a sign? Okay. So what do you want right to be? And left to be negative. Okay. So then the x component of this force here, so remember, think about the force as being the hypotenuse of the triangle. So it would be FT2, adjacent is the x side, and adjacent goes with cosine. Very good. So cosine of 45, and go ahead and put my angle in there. Then minus, because FT1 has an x component, but it's pulling left, so FT1, also cosine 45. Y direction, I've got a component of tension 1, because it's pulling left and up. I got a component of tension 2 because it's pulling right and up. I said up twice. What do you want up to be? Positive or negative? Positive. But then what about this weight force? It will be negative. Alright, so then FT1, it would be opposite of the angle, so that's sine 45, plus the FT2, sine 45, minus the weight equals 0. We made the claim that the two tensions would be equal. Well, look at this. FT2 cosine 45 is equal to, that should be equal to 0 there, is equal to FT1 cosine 45. Well, if I divide by cos 45 on both sides, what do I get? Yeah, that the FT2 is equal to FT1, which doesn't get me an answer, but it allows me to make a substitution. So if FT2 is equal to FT1, then can I substitute in FT1 there? Yeah. So then I'll have F tension 1 sine 45 plus F tension 1 sine 45. I'm going to go ahead and add the 500 to the right side. Go. Alright, so then 2 FT1 sine 45 is equal to 500. So then FT1 is equal to 500 divided by 2 sine 45. What do you get? Did you get 353-ish newtons? There you go. So if I'm using this spot where all of the forces act as the place I want to draw my free body diagram, remember, forces are vectors, and vectors are denoted with arrows. So you've got to put that little arrowhead on there, okay? So that one is, I'm going to call that one force tension 2, and it's equal to 104 newtons. Then I've got a lower angle force here, force tension 1, and it's equal to 60 newtons. And then there's a weight, and I'm just going to label it as F sub G. You can label it as M times G if you want to. That's fine. Okay. And then if this is the x-axis, which is parallel to the ceiling, then this is 30 degrees here, and this is 60 degrees here. Now, if the system is in equilibrium, then I should be able to sum up the forces in the x direction and set them equal to 0. So in the x direction, there's a 104 cosine 60 degrees minus a 60 cosine 30 degrees, and that's it. So they should equal 0. Now if you add those two up, it almost equals 0, so there's just a little bit of, I think I rounded 60 and the 104 to make it nice-ish numbers to deal with, so you don't get a perfect 0 there, you get like 0.03 or something like that, but it's close to 0. Alright, then if I sum all the forces in the y direction, they should also be balanced, and so there's a 60 Newton force component, sine 30, plus a 104 sine 60, minus the weight, which is equal to the mass of the object, times the gravitational field. And if I'm just doing a problem on paper, then I can use G is 10. but all those forces sum up to be 0. Now, if I'm looking for the mass of the object, it's buried right here, so I want to solve for that. So if you take and just 60 sine 30 plus 104 sine 60, divide that by 10, and it should be equal to your mass. Do you get about 12 kilograms?